Other than that you can do in molecular beam epitaxy. You've heard about that, right? MBE? Maybe I'll have a chance to talk about that sometimes. Okay. Other than that kind of environment, you're going to end up putting a thin layer of hydrated oxide. There is enough partial pressure of OH on there. And if it sees a free silicon surface, it would love to get in touch with each other and tie them up. Okay, that's the nature's bond. So now, you have not a problem in the industry. If I take the wafer, clean it up nicely otherwise, I always have a layer of about 1 nanometer, 10 angstroms of hydrated oxide. Do I want that? Why don't I do that? Why do you don't want that? Can anybody guess?
It prevents the SiO2 level to form.
Yes, you're right. You're right. As we warm up them to, oxidize the surface, of course, OH bonds are reasonably strong, but not very strong. And thermally, then basically I'm forming an oxide, but I may not be forming a very high quality oxide. Okay? So, industry is aware of that. They play the trick that either they strip that native layer by a HF solution, hydrogen fluoride, which grabs the, immediately dissolves into some sort of a, what do you call it, hydrated, evapors out. There's a low vapor pressure, so it goes up. Okay. And so, having done that, you have to keep that environment before you start in a controlled oxidation, so that you grow that interface with very low interface state density. Otherwise, you could have all kinds of high interface states at the interface. So what you do is you typically strip that HF clean at the very last and keep that atmosphere under control on an inert ambient. This is the easiest way to do it. Easiest way was to keep that sealed nitrogen environment until you transport that wafer to a furnace where you're going to grow oxide. And in the furnace, the loading is sealed loading. You open up that and the furnace gets sealed, and the very high nitrogen flow takes place to ensure there's no moisture can backfill somehow. No moisture can come in inside. And that way you can grow very thin oxide. When you're talking about 10, 15, 20 amps of oxide, you have to grow it very precisely, very controlled oxidation rate. It's a different rate than hydrated oxide. When you go thick oxide, you go to steam, dry, wet, dry, kind of, because then you can grow that thick oxide very quickly. And that's necessary for productivity as you throughput of your wafer. And that means more time means more expense. But when you go down to very, very thin layers of oxide, there are some special tricks industry plays to ensure the quality of that interface and a very controlled rate of growth of oxide. Okay. So that's how it works. Let's keep on going. So the native oxide, remember, that has been a challenge for us, and we solve those problems. However, there is another way of doing it. There's another way of doing it which was more elegant, and I always loved it, although I don't know if anybody commercialized it. That was a treating this requires a little more expensive system to build. And that system to build is that when you load this silicon wafers after clean, you still have an HF layer so that you don't create hydrated. But then it quickly evaporates in high temperature. But then your loading zone has a sealed plasma ozone source. A source of plasma ozone system built into in the front end of the so-called oxidation system. And what does that do? Is that as soon as it evaporates, you have a low partial pressure with a nitrogen ambient and ozone layer. And you know ozone is very active, very reactive. It's almost like ionized oxygen. And the ozone reacts immediately and forms a very beautiful monolayer with a very low interface state density. You can't even measure. And so in your so-called CV measurements, you can measure. Now, after I played with that and developed that, I asked them if they could build the furnace to do that. They said it's too expensive. I'm not going to do it. So for that. So that's another trick. So all these good attributes, right, for the oxide. So you can see how important oxide is in integrated silicon technology. It's very, very important. And no wonder we spend all kinds of fun and sweat and possibilities to do all these devices, and without the oxide, we couldn't have made the strides we made in the integrated technology. So oxide played a very important role. Okay, let's keep going. All right, we spoke about this, right? For thinner oxide, we go for dry oxide. For thicker oxide, we have a wet dry process. And typically inert gases like nitrogen and argon with extremely low partial pressure of oxygen. These are very specialized, probably less, tenth of a parts per million of moisture in these gases. It's extremely to have high quality. In nitrogen, we actually use, because of purity requirement, and typically we favor nitrogen over argon, we do liquid nitrogen source. It's liquefied all the way down to very, very extremely low temperature. So you have pure, there's no place for moisture to get in. Okay. Way below temperature. So there's all liquid nitrogen source. So important things to know that oxide kinetics are sensitive to crystallographic plane of silicon wafer. So your kinetics, the 100, which is widely used for processing in the wafer, is different than if the plane is 111. The rate of growth will be different, so that you can easily recognize which. So it depends on how the oxygen bonds in silicon and what is the silicon, spacings between that kind of thing. So it would be sensitive to crystallography. So that's kind of obvious. Oxidation involves a volume expansion. When oxide is formed, you have bigger volume because oxide you want is amorphous. You don't want crystalline oxide. Why do you don't want crystalline oxide? Tell me. Why don't you want crystalline oxide? The neighbor, yes. You know, quartz is a side too, crystalline, right? Why don't you want the crystalline?
Crystalline, they are anisotropic.
That's a good point, right? What else?
Sir, we actually want oxide to act as a barrier, sir. But oxide are really to act as a barrier, but if it is isotropic, like in crystalline, then they will at some point of time find a way, because the crystal is perfectly aligned. So they will sort of find a way to get into it. But if it is anisotropic, like it is random, sir, classroom is all randomly distributed. So someone coming in the classroom from that end to this end, they would face some obstacles and sort of sir, something.
We can get more effective area, that is not crystal, that's not crystal.
What's the difference between crystalline and amorphous? What's the difference between crystalline and solids and amorphous?
One is perfectly arranged. One is perfectly arranged, and the other one is amorphous means haphazard.
And the other one is?
Haphazardly arranged. They don't have any order.
Do you all have a little bit of course of thermodynamics, right? Do you have a course of entropy? Do you know what entropy is? What is it? What's entropy?
These are randoms.
Yes. What is nature?
Highly random.
Is nature? What is nature? Thermodynamically. What's nature?
It's constantly changing. Constantly changing.
Yeah. The ideal order is to have a very low entropy state, right? Means everything is ordered. Is nature ordered? No. Not at all. Not in the slightest imagination of us. And that's what makes us who we are. How wonderful. Can you think of this? Just think of this. We have many billion people. Each one is different. Each one is different. What would have happened if nature would have preferred to be in the lowest entropy state? We will all be the same. There will be no variation in trees. There is no variation in everything. What a terrible world that would be. Right? Now, going back to if we would have a very ordered state which is unthinkable, all crystals have imperfections. All crystals. Because the lowest entropy state cannot be achieved in nature. And can you tell me what kind of defects they have if they are trying to be a crystal? You said it. There are point defects, there are line defects, there are all kinds of defects. Okay? So, do we want that? Do we want that? No. Don't. We want to avoid that unpredictability. So that's the reason we go to a state which is a very high entropy state, amorphous insulators. So we don't have to deal with defects, we don't have to deal with grain boundaries, we deal with all kinds of things that may affect in molecular level and dimensions to alter our objective of creating an ideal device. Okay. That makes sense. Okay, oxidation involves, okay, we talked about that. Okay, optimized. Each process optimizes a fixed oxide charge, interface state density, reducing interface trap charge, mobile ion charge, bulk oxide trap to reduce the trap charge, nitridation of interface, reduce the interface state density by reducing the dangling silicon bond, ozone treatment, I spoke to you. Okay. I covered all of this. Okay, now where do we go? Dopant redistribution is another important thing. You must take into consideration that we deal with dopant in silicon everywhere, right? Play with that to make our devices work, whether it's diodes or resistors or transistors, all that kind of thing, good things. So typically these impurities, they redistribute during oxidation, which we often use after we put the dopant and we go through a thermal process, or or we have this selective area where we